This project is an investigation of the glass pane Air-Wedge interference patterns. This project was conducted by Malison Young and James Barksdale in Dr. Zhao's optics class at the University of Georgia, fall 2018. Interference is a phenomenon resulting from wave interaction. In this instance, we are observing light wave interference. Interference can be constructive or destructive, with crests and troughs of two light waves aligning to create an instance of constructive interference. The superposition of these waves at this point are the visible diffraction pattern we see on a screen. Any other point of light interaction would be categorized as destructive. Bright fringes correlate to areas of constructive interference, where dark fringes are visible where destructive interference takes place. In our experiment, we directed a red helium neon laser into our assembly. The crucial component for creating interference was a glass pane Air-Wedge. The wedge was created by introducing a small piece of paper to one end between two parallel glass panes, 25 mm by 75 mm. Data was collected for 2, 4, 6, 8, and pieces of paper in the Air-Wedge. The component was suspended for light to pass through and for interference to take place. The smartphone distance from the viewing screen was fixed. Once the screen and phone were secured, they were not moved until all necessary pictures were captured. The phone, an LG V30 Plus, was used to take images for analysis. Two calibrating images were taken to obtain the dimensions of the screen. The calibration images were found to be 1,173 by 1,090 pixels and 60.1 by 60.5 millimeters. The height was found that each pixel correlated to 55.138 micrometers. From these found values, the images were analyzed and the fringe lengths were calculated. We used a 3D printed phone stand with permission from the diffraction experiment group. The element allowed the phone to be affixed to the table at a desired and permanent position. The angle of the phone from the screen was minimized. The phone was positioned to be parallel to the screen, and the system was calibrated. We began with a level helium neon laser secured to our workstation, directed into a secured mirror at a 45 degree to the laser in order to direct the laser perpendicularly across the tabletop. Two lenses were placed in the laser's path to create a beam expander to ensure an even wave from incident on our glass panes. Once the lenses were appropriately positioned, both were secured to the table and rotation was restricted. Our glass panes were fixed parallel to each other and to a raised stand using double-sided tape, and once they were aligned to be perpendicular to the beam path, securing the stand to the table. To get varying data points, multiple sheets of paper were inserted between the edge of our glass panes. In the path of our reflected beams were placed our viewing screen, constructed of a cardboard frame and the translucent lens cleaning paper. On the opposite side of where our viewing screen was fixed, a smartphone was placed into a 3D printed device to hold it in a constant position and angle in relation to our viewing screen. In our experiment design, there were two errors we believe were most like to present that we could minimize: debris on our glass panes and shifting of the individual sections of our setup. To ensure minimal interference from debris on all of optical devices, all were wiped down with a lens cleaning cloth initially and were handled solely with gloves later in the lab. We could not, however, account for any minor imperfections in our devices or the possibility of dust mites landing on them later. All individual pieces of our setup were firmly secured into the table and were applicable. Any rotating pieces had their screws tightening to ensure they were not bumped out of alignment later on. A portion of the beam transmitted through the glass to form a round beam on the wall behind the commode. The remaining portion of the wave was reflected onto a screen 95.62 centimeters away. The screen was constructed using 2 cutout cardboard frames and a secured, suspended Chemtech wipe between them. The screen was secured to the table and the wipe was pulled taut, making it smooth and allowed for crisp, consistent images of the interference pattern to be taken. The images were taken by a smartphone affixed to a 3D printed component used with permission from another group. The 3D printed component was affixed to the bench with 5 hex head threaded screws to keep both the angle and the distance of our camera to the viewing to the screen unchanged. We believe the unintentional compression of the sheets of paper is the predominant source of error in our measurements. This conclusion was reached based on the consistent decrease of individual average paper thickness with each increase in the number of sheets. With each data measurement, the pressure from the wedge would increase and the time some of the sheets were under this pressure would increase. We did not consider the impact of this error in our initial experimental design, and if we repeated this procedure, we would exchange our papers for each new data measurement, as well as make an active effort to avoid placing any additional pressure on our glass wedges. Slides from Dr. Zhao's lectures were referenced, and the formulas that were used to find thickness include D equals AX and XM equals 2M plus 1 times lambda 2 over 4A. To ensure that our conclusions were true in a variety of situations, data was collected for 2, 4, 6, and 8 pieces of paper wedged. The data was then compiled and investigated. We cropped each image down to a section containing only 10 clear fringes. We then divided the pixel amount of each cropped photo by 10 to get our resulting pixel length per individual fringe, and multiplied that by our measurement of corresponding length of our screen per pixel. After fitting our results, it was found that the measured paper thickness was 0.05 millimeters, or 50 micrometers. The images are shown here of 10 fringes for 2, 4, 6, and 8 pieces of paper. The intent of our Air-Wedge experiment was to find precise measurements of thicknesses for multiple sheets of paper. We then compared our measured results for the thickness of standard printer paper to an accepted value of thickness we found online of about 50 micrometers. To make sure we had multiple data points to draw from, we measured the thickness of 2, 4, 6, and 8 sheets of paper, and then later divided the total thickness of each group by the quantity of papers to find the average thickness of individual sheets of paper. Our measurements of average paper thickness resulted in quantities ranging from 45.4 micrometers to 49.8 micrometers, with the former being the average thickness of 8 sheets of paper. It is our belief that the decrease in average thickness was caused by paper compression from our wedge. These measurements of thickness have an average experimental percent error of negative 4.9%. Accounting for the compression we believe we observed, this is an acceptable percent error for our measurements.